Time does not simply pass. It arrives grain by grain, like light filtering through the ribs of a cathedral. In the dark before the first dawn, there was no before, no ticking metronome to count a path through emptiness. There was only a boundary where equations stumble, a horizon where language fails. The universe woke, and with it duration itself. Moments learned to stand in line, causes learned to precede effects. If space is the stage, time is the silence that lets the first note exist. Yet at the origin, that silence becomes paradox, a singular point in general relativity where distances shrink to nothing and clocks cannot be built, a quantum fog where uncertainty shreds continuity, a place where when has no purchase. Physicists have traced the universe back to unimaginably hot fractions of a second, each flicker scaffolding the world we inherit. Nuclei coalescing, light decoupling, galaxies pegged to an expanding loom. And still, the question remains like a star just below the horizon. How did time begin? Did it bloom from a quantum seed, smooth itself across an inflating sky, and leave an arrow pointing outward from a primordial stillness? Did it emerge from entanglement, a rhythm born of relations rather than an absolute beat? Or does it run in two directions from a shared cradle, a mirror universe advancing into its own future, which is our past? To ask how time began is to press one's ear against the wall of reality and listen for the first breath. The answer, if it exists, will be written in fossil light, in ripples of gravity, in the statistics of ancient hydrogen, and in the limits of what we can mean by begin. In the oldest nights, time was counted by flame and sky. Shadows lengthen across stone as constellations wheeled with a patience older than language. Farmers read the seasons in the slow drift of sunrise along a horizon of hills. Priests tallied days by the crescents and disks of the moon. Navigators trusted the metronome of stars to cross deserts and oceans. In those arrangements of light, time appeared not as a substance but as pattern, an order stitched to the heavens. Calendars were carved from this rhythm, lunisolar almanacs aligning months to harvests, intercalary days inserted to reconcile the quarrels between sun and moon. From Babylon to Mesoamerica, from the Nile's reliable flood to the Roman reform that fixed months into an imperial schedule, chronology matured as a sky-measured discipline. Time, at first, was the choreography of celestial bodies, not an independent river. The age of mechanisms changed the texture of hours. In the 17th century, regularity stepped down from the vault of the firmament and swung from a thread. Galileo studied the pendulum's near-isochronism, the surprising steadiness of its period despite small changes in amplitude, and with that finding separated duration from the vagaries of human attention. Christian Huygens then caged this regularity inside brass and escapements, building the pendulum clock in 1656 and sharpening the world's seconds to a new edge. Bells in town squares no longer sang merely of devotion or decree. They etched intervals with a reproducible beat. Time began to look portable, measurable anywhere, no longer hostage to the clouds or the priestly lens. The mathematics of motion rose upon that metrical foundation. In Isaac Newton's Principia, planets obeyed a law that unfurled cleanly only when cast against a uniform backdrop. He named that backdrop absolute, true, and mathematical time, a universal flow that neither hastened nor slowed, indifferent to the histories it held. Simultaneity was assumed as common currency. Events could be labeled with the same now, regardless of their distance. Space, too, was absolute, an infinite grid ready to receive coordinates. Within this architecture, the calculus of forces and trajectories achieved astonishing reach. Comets anticipated, tides explained, cannon shot predicted. The century learned to trust that change could be measured against a silent, invisible river. But the river showed eddies where none were expected. In the 19th century, James Clerk Maxwell braided electricity and magnetism into a single field theory and found in its equations a constant speed for waves, light's own velocity, set by nature and not by any source. If light's speed was invariant, what anchor determined it? The ether was proposed as a subtle medium, an invisible lattice against which motion could be judged. Yet when Albert A. Michelson and Edward W. Morley turned their interferometer in 1887 to detect the ether wind, the result was stubbornly null. No preferred drift revealed itself. The apparatus insisted on symmetry where a background had been presumed. The old absolutes began to fray. In 1905, Albert Einstein cut the frayed strands and rewove them. He took the invariance of light speed not as a puzzle to be explained away but as a principle to be obeyed, and from that fidelity he built special relativity. Time dilated for the swift, lengths contracted in the direction of motion, simultaneity fractured into frames. Without a universal now, the river was no longer single but braided, each observer carrying a proper time that measured the intervals along her world line. 2 years later, Hermann Minkowski gave this physics its geometry, fusing space and time into a four-dimensional manifold where intervals replaced absolutes and light cones governed what could influence what. Einstein carried the insight further. He recognized that gravity need not be a force tugging across a void but a curvature in spacetime itself, sculpted by mass energy. In 1915, general relativity completed that transformation. Clocks ticked differently in valleys than on mountain tops. Light curved around suns. The perihelion of Mercury processed just so. Time was no longer the stage. It was part of the choreography. Geodesics told matter how to move. Matter told spacetime how to curve. A new question surfaced from the equation's depths. If time is geometry, what is its shape on the largest scales? The answer would not come from a fixed, eternal firmament. Alexander Friedmann, working in the early 1920s, discovered that Einstein's field equations allowed dynamic solutions, universes that expand or contract. Georges Lemaitre, a Belgian priest and physicist, connected the mathematics to the sky, proposing in 1927 that galaxies, redshifts betray cosmic expansion and suggesting a primeval atom, a compressed beginning from which space and time themselves unfurled. In 1929, Edwin Hubble's observations of distant galaxies revealed a linear relation between distance and recession velocity. The cosmos was not a static cathedral but a balloon whose fabric stretched, carrying galaxies apart like painted dots moving with the rubber. Within this architecture, a special parameter emerged: cosmic time, the proper time kept by observers riding the Hubble flow, each commoving with the expansion. In the simple, symmetric world of the Friedmann, Lemaitre, Robertson, Walker metric, cosmic time could be defined globally, aligning clocks across the largest possible vista. Evidence gathered like ash that still held the imprint of fire. If the early universe had been dense and hot, it should have forged light elements in calculable proportions during its first minutes. The theory of Big Bang nucleosynthesis predicted a cosmos dominated by hydrogen, salted with helium-4 and traces of deuterium and lithium. Later, as the plasma thinned and cooled, photons would break free from matter, leaving behind a fossil glow, a cosmic microwave background stretched by expansion into microwaves. In the late 1940s, George Gamow, Ralph Alpher, and Robert Herman estimated this afterglow's temperature. Their prediction waited in the cold sky until 1965, when Arno Penzias and Robert Wilson, tuning a radio horn antenna in New Jersey, met a persistent hiss they could not scrub out. It was the sky itself, 2.7 Kelvin above absolute zero, whispering from 380,000 years after the beginning. Later satellites, COBE, WMAP, Planck, transformed that whisper into a detailed map of temperature and polarization, showing a nearly uniform bath with tiny ripples, the seeds of all future structure. The patterns near scale invariance and Gaussian statistics suggested quantum fluctuations stretched to cosmic size, hinting at an episode of accelerated expansion, inflation, that smoothed horizons and flattened space. Yet beneath the success of this narrative, the equations point to a cliff. Run the expansion backward and densities surge. Temperatures climb. The scale factor shrinks. Under broad conditions, positive energy density, reasonable causal structure. The Hawking, Penrose singularity theorems imply that time-like geodesics cannot be extended arbitrarily into the past. In general relativity's classical architecture, there is an edge to the story, a boundary where curvature diverges and the notion of earlier fails. The river of time, tracked faithfully by commoving clocks, reaches a headwater that is not simply a physical point but a limit of theory. It is an honest confession written in mathematics. Beyond this line, classical spacetime offers no further pages. The gravity of beginnings does not draw only cosmologists. Black holes, predicted by the same theory, braid time with thermodynamics in a way that complicates every intuition. Jacob Bekenstein proposed that a black hole possesses entropy proportional to the area of its event horizon, not its volume, a bookkeeping of information about states hidden from the external universe. Stephen Hawking's quantum calculation then revealed that black holes radiate with a temperature inversely proportional to their mass, slowly evaporating over unimaginable periods. Gravity had acquired a thermodynamic accent. Horizons, whether cosmic or compact, carried temperature and entropy, knitting information, geometry, and heat together. In this tangle lies a deeper arrow of time. Entropy tends to increase, yet in a universe born from extraordinarily low entropy, as observations seem to demand. Why was the initial gravitational configuration so special? Why was the early cosmos smooth enough that its Weyl curvature, a measure of tidal gravitational degrees of freedom, was effectively near zero? Each development in this discovery arc tightens the central riddle rather than loosening it. The ancients gave time a face in the sky, clocks gave it a pulse, Newton gave it an axis, Maxwell and Michelson, Morley shook its absolutes, Einstein and Minkowski gave it geometry, cosmology gave it a history, radio horns and satellites captured its infant light, singularity theorems drew a boundary around its origin, black hole thermodynamics entangled it with information's arrow. The narrative converges toward a horizon that is both mathematical and metaphysical. If time is born with the universe, what does birth mean when the midwife is a differential equation? The instruments continue to trace the aftermath of that birth with mounting precision. The microwave background's acoustic peaks speak of baryons and photons locked in a primordial dance. The standard candles of supernovae mark the later acceleration of expansion. Large-scale surveys map the cosmic web that grew from quantum tremors preserved as initial conditions. On the highest mountaintops, optical lattice clocks now compare seconds with such fidelity that height differences of centimeters register as gravitational redshift. Even the notion of time's uniformity is tested, as laboratories and pulsars together search for minute drifts in fundamental constants. Yet all these achievements point past themselves to a shared silence, the initial boundary where geometry, matter, and quantum uncertainty must be reconciled. This is the discovery phase not in the sense of solving a puzzle, but in the sense of circling a singular fire. Each step, calendar, pendulum, absolute parameter, finite signaling, relativity, expansion, afterglow, entropy, casts new light on the same core shape and reveals a deeper shadow at its center. The universe has provided fossils of its own chronology, a skywide photograph taken in childhood elemental ratios from its first minutes, the present expansion that remembers an ancient push. The evidence is coherent and the story powerful, yet the first sentence remains partially redacted. Time, it seems, is both the subject and the artifact of the investigation. It structures discovery while remaining the most mysterious discovery of all. In that duality lives the quiet astonishment of modern physics. The cosmos, by beginning, allowed clocks to exist, and those clocks return the favor by reading the strata of that beginning. The same equations that bend light around a star insist that, under the conditions of the early universe, extension into the past reaches an end. Somewhere between the smoothness of the microwave sky and the roar of Planck-scale fluctuations, between commoving proper time and evaporating horizons, the language of nature shifts dialect. The chapter closes not with an answer but with a threshold, a recognition that the history of time has been reconstructed down to the point where history, as physics usually tells it, can no longer speak. The shock arrives where the map runs out. General relativity, so precise that it bends starlight by the predicted arc minute and times the dance of pulsars to fractions of a microsecond, draws a clean line at the beginning and steps back. At t right arrow 0, its confident geometry unspools. Curvature races toward infinity, densities toward the unimaginable, and the very paths that clocks follow, time-like geodesics, are declared incomplete. The singularity in this language is not a thing. It is a confession. It marks the point where the theory, triumphant across galaxies and black holes, no longer knows how to tell a story. The boundary is not a wall of matter but a limit of description, a place named by mathematics to warn that spacetime, as treated classically, cannot be extended further into the past. This collapse is not caprice. The Hawking-Penrose theorems, resting on modest assumptions about energy and causality, show that under broad, physically reasonable conditions, an expanding universe like this one must harbor an initial boundary. The price of gravity's elegance is paid at the edge. Follow the expansion backward and the fabric tightens until the threads cut into one another. The horizon of predictive power contracts. No coordinates can be stitched that run cleanly through t equals 0. A law that has guided spacecraft to distant planets bows out at the first instant and leaves an unanswered question in its wake. If time is geometry, what is the geometry of the beginning? The cosmos amplifies the challenge with a separate, quiet astonishment. The microwave sky, mapped to exquisite detail, is almost perfectly uniform in temperature. A blackbody glow at 2.725 Kelvin, modeled only by ripples of order 10-5. Regions separated on the sky by tens of degrees display nearly the same thermal history. Yet at the epoch when this light last scattered, from a plasma that had just cooled enough for atoms to form, those regions were too far apart for any signal, even light, to have crossed between them. Causal contact could have synchronized only patches about a couple of degrees wide on the celestial sphere. The rest should bear independent thermal quirks. Instead, the sky is astonishingly even, with only subtle acoustic fingerprints laid down by gravity and pressure waves in the infant plasma. The horizon problem is the name given to that precision uniformity across expanses that, in standard Big Bang evolution without an earlier dynamical mechanism, could not have shared information. It is a puzzle written not in one anomalous point, but in the overwhelming sameness of the whole. There is another razor's edge concealed in the same data. On the largest scales measured, the geometry appears nearly flat, Euclidean to an accuracy that startles. In Einstein's equations, the ratio of actual density to the critical density, omega, determines whether space is open, closed, or flat. If omega differs even slightly from unity in the early universe, the difference grows with time. To give rise to the near flatness seen today, omega at early times must have been set to unity with absurd precision. At the Planck time, the allowed deviation would have been tuned to something like 1 part in 10 raised to 60, or better, numbers that strain the notion of a natural, unguided initial condition. This flatness problem is not an aesthetic complaint. It is a statement that, without new early universe dynamics, the initial curvature had to be prepared by hand to an extraordinary degree. The uniformity and the flatness lead back to a deeper and more intimate enigma, the arrow of time. Every life, every memory, every burning star rides an asymmetry that points from past to future, codified in the second law of thermodynamics. Entropy tends to increase, but an arrow needs a fletching. For entropy to climb, it must begin low. And not just low in the tally of thermal motion, the gravitational degrees of freedom matter most. A smooth early universe with tiny density fluctuations possesses remarkably low gravitational entropy. There are few ways to arrange mass energy into such evenness. The future is generous. Galaxies, stars, and black holes provide countless high-entropy states, but the past, by the evidence of the sky, was exquisitely special. This claim, often called the past hypothesis, is not a mechanism but a boundary condition, the blueprint that says the universe started in a state from which disorder could grow. It solves no equations, it simply sets the initial page. Why the page was so clean remains unexplained within the standard hot Big Bang model. The shock grows sharper at the seam between physics, two great languages. General relativity speaks in smooth curves and continuous metrics. Quantum theory speaks in amplitudes and probabilities, in superpositions that evade classical description. Extrapolated backward, the expansion rushes into the Planck regime, around 10 raised to negative 43 seconds after the putative beginning, or the Planck length. 10 raised to negative 33 meters and Planck energy set the scale. Their quantum fluctuations of geometry itself should matter. Yet no complete quantum theory of gravity, tested by observation and calculation with the same authority as its parents, stands ready to replace the classical script. The early universe thus sits at a fracture, the laws that govern atoms and light, and the law that governs spacetime, both essential, both incomplete in the same instant. Cosmology becomes a palimpsest, where equations are legible in parts and smudged in between. At the philosophical boundary, time's nature complicates the physics it organizes. In relativity, past, present, and future are not universal shelves but frame-dependent slices through a four-dimensional manifold. Many working pictures of spacetime resemble a block in which all events coexist structurally, while the felt passage of time, its flow, finds no simple corollary in the equations. Quantum mechanics brings a counterpoint. Measurement appears to pick a single outcome from a spread of possibilities, and the probabilities evolve with a parameter called time. Whether that collapse is fundamental or only apparent through decoherence, whether time's arrow derives from boundary conditions or from entanglement structure, remains under debate. The Planckian origin of time therefore rubs against two distinct puzzles: how to quantize geometry without destroying causality, and how to reconcile the lived asymmetry with theories that, at their core, are largely time-reversal symmetric. Even the word nothing proves treacherous when clocks are allowed into the conversation. A physical nothing, in modern field theory, is not absence but vacuum, a state with no particles yet restless with quantum fluctuations, fields at their lowest energy still jittering around a baseline. In some models, vacuum can possess different energy densities and can transition between them, releasing latent energy into particles and radiation. In others, geometry and fields are so tightly coupled that a change in one is a change in the other. To ask why there is something rather than nothing is to ask which of these vacua is realized, why its energy has the value it does, and why the constants that regulate the strength of forces and the masses of particles fall into the narrow ranges that permit chemistry, stars, and long-lived structures. The presence of clocks, the possibility of stable periods, repeatable frequencies, coherent oscillations, depends on those values. A universe whose parameters stray far from the measured ones would allow no durable rhythms, no recordable causality. The question is not only why there is being, but why there is ordered becoming. The data offer no easy escape. The cosmic microwave background's exquisite uniformity and its tiny, nearly scale-invariant ripples suggest an early dynamical agent that expanded space faster than light can cross it, an inflationary episode that irons horizons flat and drives omega toward unity. Yet even that solution, successful in describing large swaths of observation, raises new beginnings. A field must be poised high on a potential, smooth across a region already larger than the Planck scale, and capable of ending gracefully to reheat the universe. If inflation is eternal in some realizations, spawning pocket universes with varying properties, the question of initial entropy and the arrow is displaced rather than erased. A meta-beginning looms, asking for a measure on the ensemble. If inflation did not happen, An alternative mechanism must still account for the same stubborn facts whispered by relic light. Elsewhere, gravity's thermodynamic accent refuses to dim. Horizons radiate as if they have temperatures. Their areas count microstates in a way still only partially understood. If information is never lost, as quantum mechanics insists, then evaporating black holes must return it somehow, transforming what looks like irreversible thermal glow into correlations subtle enough to preserve unitarity. The information paradox is born from the same mathematics that predicts singularities and cosmic expansion. It threads black holes and Big Bang together into a single tapestry. Where information goes in the presence of horizons may rhyme with how information was initially arranged at the cosmic beginning. A low-entropy past is, in effect, information packed into a simple macrostate. How that packing occurred is the unresolved preface to every arrow drawn since. The laboratory does not stand indifferent. Atomic clocks now compare seconds so sharply that moving one a few centimeters higher in Earth's gravitational potential registers a measurable redshift. Networks of such clocks test whether the constants of nature drift with time or position. Particle colliders probe fields that might have driven the earliest accelerations. Neutrino experiments worry at the mass hierarchy that could be entangled with cosmological initial conditions. Pulsar timing arrays sift for a gravitational wave background that might carry faint syllables from primordial processes. Each effort sharpens the outline of the problem without yet filling the center. The shock, then, is layered. It begins with the admission that Einstein's masterpiece cannot be continued to the first instant. It gathers strength in the sky's unnatural uniformity and the universe's precarious flatness. It deepens with the realization that all arrows point away from a past improbably pristine. It hardens at the joint between quantum and classical law, where the grammar for geometry and the grammar for matter cannot yet be spoken together. And it settles into the philosophical marrow of the question, not merely why there is something rather than nothing, but why there is a world in which cause can precede effect, in which clocks can keep honest time, in which memory can be written, read, and believed. In that recognition lies the chapter's quiet verdict. The beginning is not only a point where calculations fail, it is a mirror held up to the expectations of completeness. The cosmos, so generous in evidence, has left traces that demand a deeper narrative, a mechanism to smooth horizons, a reason for flatness, a boundary condition for entropy, and a unifying language for geometry and quanta. Until such a narrative stands, the first instant remains both present and withheld, a bright edge at which law dissolves into question, and the measure of time itself waits to be explained. The patient cartography of the early universe began with a whisper and became a map. Kobe first heard it, a nearly perfect blackbody glow, 2.7 Kelvin above absolute zero, ruffled by temperature ripples so slight that their imprint lay at 1 part in 100,000. WMAP sharpened the contours, tracing the faint mottling across the entire sky and revealing a spectrum of fluctuations that looked almost scale invariant. Larger waves only slightly stronger than smaller ones, and astonishingly Gaussian, as if drawn from a single, simple random process. Then Planck arrived and pressed the cosmos under a finer lens. Acoustic peaks, regular crests in the power spectrum, stood out like harmonic notes from a drum once filled with light and baryons. Their spacing and heights fixed the cosmic recipe. How much ordinary matter, how much dark matter, how fast the universe expanded, how curvature bowed or did not bow the largest scales. The first peak's position spoke of near-flat geometry. The relative heights told of baryon inertia against photon pressure. The damping tail whispered of diffusion where photons smeared imperfections into silk. Polarization patterns added a second alphabet to the narrative, allowing a cross-check of temperature data and a route to the earliest possible imprints of gravity itself. From these skywide hieroglyphs, early time physics emerged not as myth, but as measurement. On larger canvases, the same sound left a fossil ridge. In the young plasma, Gravity and pressure set up waves that marched outward until the cosmos cooled and recombination stilled the drum. The distance those waves traveled, about 150 megaparsecs in comoving units, froze into the distribution of matter as a preferred scale, later to be read in the clustering of galaxies. Surveys, SDSS and its boss and EBOSS successors, and now ever deeper campaigns, found the faint excess of pairs at that separation, a standard ruler threaded through three-dimensional space. Baryon acoustic oscillations, measured across cosmic time, became a yardstick for the expansion history, confirming the tale told by the microwave background and stitching late-time structure to early-time sound. The web of galaxies thus became another clock, recording how cosmic time's scaffolding grew from a feature etched when the universe was young. Closer to the first minutes, the cosmos practiced a chemistry so simple it can be calculated on paper, yet so precise it can test entire frameworks. Big Bang nucleosynthesis predicted that a hot, expanding fireball would leave behind a universe dominated by hydrogen, accompanied by roughly a quarter helium by mass, and trace isotopes, deuterium, helium-3, and lithium-7, in amounts exquisitely sensitive to the early expansion rate and the density of baryons. Observations of ancient gas clouds backlit by distant quasars, of metal-poor stars, and of the microwave background's acoustic peaks converge on a picture in which deuterium acts as a chronometer. Change the expansion or the number of relativistic species in those first minutes, and the deuterium abundance shifts. The concordance between light element predictions and measurements anchors the early timeline. A stubborn tension persists in lithium, a problem that could be nucleosynthetic nuance or stellar alchemy at work, but the broader message remains. The first minutes were governed by known physics, and their relics still answer across billions of years. Where the sky grows quiet, it also grows demanding. If a brief, violent episode of accelerated expansion, cosmic inflation, stretched quantum fluctuations to astronomical size, then space should carry the fingerprints of primordial gravity. Those fingerprints would curl the polarization of the microwave background into a faint B-mode swirl, a pattern distinct from the even parity ripples laid down by density waves. Experiments at the poles and on mountain plateaus have searched for that signature, with instruments tuned to measure temperature differences smaller than a millionth of a degree. The signal remains elusive. Dust in the Milky Way mimics the twist. Lensing deflects photon paths to generate B-modes from E-modes, and nature so far has offered only upper bounds on the ratio of gravitational to density waves. Each non-detection is a ruler of a different kind, pressing the energy scale of any inflationary epoch downward, pruning families of models that predict too much gravitational roar. If the tensor whisper ultimately proves beyond reach, either inflation occurred at a gentler pitch than many expected, or the beginning chose a different melody altogether. Elsewhere, the universe offers hints that do not yet compose a theme. Experiments tuning their ears to the 21-centimeter line of neutral hydrogen, a radio whisper that tracks the temperature and ionization of the intergalactic medium, have begun to probe the unlit centuries after recombination, when the first stars kindled and bathed the cosmos in ultraviolet light. Acclaimed global absorption feature deeper than simple models predicted set imagination racing toward exotic possibilities, interactions between baryons and dark matter cooling the gas, or radio backgrounds brighter than assumed. The result remains contested, and the field moves cautiously toward images of the cosmic dawn, with arrays like Hera and Pathfinders to the square kilometer array, which aim to map the three-dimensional evolution of hydrogen through time. If the signal yields to clarity, it will offer a new lever arm into the first billion years, where deviations from standard expectations may trace their ancestry to physics closer to the beginning. At the same time, the sudden appearance of surprisingly bright, surprisingly early galaxies in deep infrared surveys has provoked a reconsideration of how quickly structure can assemble. If masses inferred at redshifts greater than 10 are confirmed and systematics tamed, then star formation and halo growth may be more efficient under primordial conditions than standard models assumed, or the initial power spectrum may carry subtle features that grant small scales an early start. The tensions today are as much about modeling and measurement as about theory, but they serve the larger pattern. The deeper the look, the thinner the margin for the earliest physics to hide. Some fossils do not shine, they hum. Gravitational waves carry information with a stubborn honesty, immune to scattering by matter or the fog of charged particles. A universe that inflates, that undergoes phase transitions, that births and snaps cosmic strings, that shakes with anisotropic stresses in its first instance, will set the spacetime sea to trembling. Ground-based detectors, LIGO, Virgo, KAGRA, have already tuned into the cataclysmic chirps of black holes and neutron stars, and with them constrained any loud, broadband background that might have ridden in from the early universe. Their silence at certain frequencies tightens bounds on cosmic strings and rules out especially vigorous early time processes. Space-based observatories in design LISA, and farther on, third-generation ground detectors like the Einstein telescope and Cosmic Explorer promise sensitivity to longer waves, where cosmological backgrounds might live. Murmurs from phase transitions in the first fractions of a second or a fossil spectrum spawned by whatever mechanism smoothed the horizon. If detected, such a background would be less a message than a fingerprint, yet even a fingerprint can narrow suspects to a few. Other windows open through particles that barely notice matter at all. Neutrinos streamed free when the universe was seconds old, and their relic background should fill space even now, colder than the microwave photons and nearly impossible to touch. The effective number of relativistic species, NF, inferred from the microwave background and light element abundances, currently hugs the standard model's expectation, leaving little room for hidden light relics, but not eliminating them. A direct detection of the cosmic neutrino background, sought by audacious proposals like Ptolemy, would turn theory into measurement and provide a new anchor for the expansion history and the thermal ledger of the first seconds. The sum of neutrino masses, traced indirectly in the way structure grows and small scales wash out, connects laboratory oscillation experiments to the formation of galaxies. Any sterile cousins would shift that connection and bend early time inferences. Beyond neutrinos, a dark radiation component, any light, weakly coupled species, would tilt the early clock, hastening or slowing time's first beats in a way precision cosmology can, in principle, hear. Yet the most exacting tests of time may be local. Optical lattice clocks, trapping atoms in grids of light, now count seconds with fractional uncertainties of parts in 10 raised to 18 and beyond. Lift one a centimeter and gravity stretches its seconds enough to measure. Link many across continents, and they become an interferometer for time itself, sensitive to passing gravitational waves at frequencies higher than pulsar timing arrays and lower than ground-based laser interferometers, and to any slow drift in the constants that set the length of a second. Networks of such clocks probe Lorentz invariance and CPT symmetry, asking whether the speed of light is the same in all directions to within unimaginable precision, and whether matter and antimatter obey the same temporal grammar. In the skies, violent flares from gamma-ray bursts and the heartbeats of millisecond pulsars become natural laboratories. If high-energy photons or neutrinos arrived measurably earlier or later than their low-energy kin after crossing billions of light years, it would hint at a granularity in spacetime or a violated invariance. So far, nature has kept the beat, and null results have become pillars that hold up continuity. Together, these lines of inquiry weave a single pursuit from many threads. The microwave background turns the infant universe into data. Galaxy surveys measure the growth of cosmic bones. Light-element ratios time the first minutes. Polarization maps test for a gravitational whisper from the beginning. Radio arrays chase the afterimages of the first stars. Gravitational wave detectors open a sound channel to physics that never glowed. Neutrinos and potential light relics calibrate the thermal ledger. Clocks and distant beacons ask whether time's rules vary across height or history. Each instrument homes in on a different page of the same prologue. Each negative result narrows the corridors that the origin can have walked. Each anomaly, if confirmed, will redraw the foyer where time enters. The picture that emerges is neither finished nor formless. It has the symmetry of near-scale invariance and the discipline of Gaussian statistics. It has the crisp ruler of baryon acoustic oscillations and the chemical memory of deuterium. It has the sternness of upper bounds on primordial tensors and the openness of contested whispers at radio wavelengths. It has the silence of absent stochastic hums and the promise of detectors yet to fly. These are not decorations on a theory. They are the rails on which a single mystery moves. If time began with a mechanism, an inflating field, a bounce, a no-boundary glide, a quantum transition from a state with no classical before, its residue must be inscribed in one or more of these ledgers. The deeper the measurements reach, the fewer places a beginning can hide. In the quiet between data releases and sky surveys, one truth remains steady. The early universe, once a metaphysical question, has become an empirical enterprise. It gives answers in photons and in waves, in chemical ratios and in the syncopation of clocks. What is sought is not simply a timestamp for the first moment, but the grammar by which moments came to exist, the rule that made causality possible, that permitted memory, that allowed the cosmos to carry a history at all. The investigations move with the same patience as the light they study, across deserts, across mountaintops, through space, through time, toward a beginning that will be known not by metaphor but by measure. The first fracture appears as a number that refuses to agree with itself. On one side of the timeline, the early universe whispers a value for the cosmic expansion rate from the geometry of its fossil light. On the other, nearby galaxies, measured with stellar yardsticks and supernova beacons, speak a faster rhythm. The disparity is small in sound, large in meaning. If the cosmos expands more briskly now than the microwave background alone would predict, then something unaccounted for stirred the plasma before atoms first formed, an ingredient present in the pre-recombination recipe, yet absent from the standard list. The Hubble tension is the modern name for this hairline crack. It is not a verdict of error, though systematics are hunted with relentless care. It is the possibility that the origin of time left an aftertaste in today's expansion. The distance ladder builds upward from parallax, trigonometry written by Earth's orbit, to Cepheid variables with periods that calibrate their luminosities, to type Ia supernovae that standardize whole galaxies at once. Independent anchors, masers orbiting black holes, the tip of the red giant branch, strong lensing time delays, reassert the pace. Meanwhile, the early universe inference comes from the acoustic peaks of the cosmic microwave background, a relic whose pattern encodes the density of matter and radiation, the curvature of space, and the scale of the sound horizon when the cosmos was young. Connect that ruler to late-time baryon acoustic oscillations, and the standard model returns a slower expansion today. Between the two regimes lies a silence that may be a message. Early dark energy, briefly adding pressureless fuel before recombination. Additional light relics subtly quickening the first minutes. Altered recombination physics changing how photons decoupled. Even more exotic couplings that nudge the sound horizon smaller. Each proposal tries to smooth the fracture without shattering the rest of cosmology. If the tension holds under new measurements, it will not merely fix a number. It will push the story of time's beginning to include a brief chapter of unfamiliar dynamics, written into the first 300,000 years. Beneath the arithmetic runs a deeper unease. The arrow of time, the universal drift from ordered beginnings toward tangled aftermaths, presumes a special start. Thermodynamics demands it. Entropy grows because there are more ways for matter and radiation to be disordered than arranged. The future is spacious, the past selective, but gravity complicates the tally. A clumpy universe with black holes has far greater gravitational entropy than a smooth one. High curvature and horizons multiply microstates. The microwave background's near-uniform glow therefore testifies to an incredibly low gravitational entropy at the outset, a near-vanishing whale curvature that left little room for tidal distortions. Roger Penrose gave this observation its sharpest form. The primordial state seems tuned with astonishing precision toward geometric simplicity. No mechanism within the standard hot Big Bang sets that condition. It is taken as given. The arrow thus points away from a boundary that the theory does not generate. The architect of low entropy is missing from the blueprints. Attempts to make the edge less abrupt do not remove the questions. They rename them. Quantum gravity proposals have learned to dodge singularities that general relativity cannot. Loop quantum cosmology replaces the classical divergence with a bounce. Quantum geometry sets a maximum density and turns collapse into expansion. Ekpyrotic models use a slow, ultra-stiff contraction to iron away irregularities before a transition births the hot universe. The Hartle-Hawking no-boundary proposal smooths the origin by rotating to a Euclidean phase where time behaves like a spatial coordinate, joining the first moment without a sharp seam. Tunneling from nothing scenarios describe the universe as a quantum fluctuation that classicalizes into spacetime. Each picture trades the singularity for a new kind of beginning, an earlier phase, a boundaryless cap, a probabilistic nucleation. But each still must explain why the initial condition of that earlier phase is low entropy and smooth, why the transition yields the arrow seen since. Averted infinities do not automatically generate order. There is a symmetry temptation that runs in parallel. If the microscopic laws are largely time reversal invariant, why not imagine a cosmos that mirrors itself across the origin? In CPT-symmetric scenarios, the Big Bang is not an asymmetrical start but a junction, with two universes expanding in opposite temporal directions from a shared low-entropy surface. In such models, particles in one half correspond to antiparticles in the other. The combined whole satisfies the deepest discrete symmetries. The arrows of time point away from the junction on both sides, much as entropy increases in either direction from the crest of a hill. This picture offers elegance. The specialness at the origin is encoded as symmetry rather than chance. It also courts testable hints, relations among neutrino properties, dark matter candidates born from the structure of symmetry itself, specific absences in primordial gravitational waves. Yet even here, the philosophical core persists. Does symmetry alone account for the extraordinary smoothness, or does it merely reframe the selection? Beneath these structural debates runs an argument about reality's fabric. Horizons, cosmic or black hole, behave like thermodynamic systems, with temperatures and entropies measured not in volumes but in areas. In quantum gravity's most persuasive laboratory, the holographic duality between certain gravitational theories and lower-dimensional quantum field theories, geometry, is a translation of entanglement. The Ryu-Takayanagi prescription and its covariant extensions relate areas of extremal surfaces in spacetime to the entanglement entropy of regions in the boundary theory. More recently, the island, formula, and replica wormhole techniques have recovered the expected page curve for evaporating black holes, reconciling Hawking radiation with unitary quantum mechanics by allowing spacetime topology to participate in bookkeeping. These advances whisper that spacetime, and the time within it, may be emergent from patterns of quantum information. If so, the beginning ceases to be an explosion in a pre-existing arena and becomes a phase transition in the grammar of entanglement, an onset of connectivity that makes notions like distance, duration, and causality meaningful. The question, how did time begin, shifts register. What dynamics turns quantum correlations into a macroscopic arrow and a classical clock? Observations continue to pull on every thread. If an early dark energy episode explains the Hubble tension, then subtle shifts should appear in the microwave background's polarization and lensing. in the clustering of galaxies, in the statistics of the Lyman alpha forest. If additional light relics altered the expansion, the effective number of neutrino-like species should edge upward, with consequences for element abundances and structure formation. A confirmed primordial gravitational wave background, by CMB modes, by pulsar timing arrays, or in the longer wavelengths of space-based detectors, would anchor the energy scale of pre-recombination physics and narrow the space of beginnings to those loud enough to shake spacetime. Conversely, an enduring silence would favor low-energy onsets or non-inflationary smoothers. High-redshift galaxies, if truly too massive too soon, would tug the initial power spectrum away from a simple scale-free form and expose features from processes closer to the first instant. Each anomaly demands several crosschecks. Each crosscheck, if passed, will harden a hint into a boundary condition on origin stories. Meanwhile, clocks on Earth expose the delicacy of time itself. Optical lattice clocks compare seconds with such acuity that lifting one by a fingertip's breadth changes its rate observably. Networks of these devices already test Lorentz symmetry and search for drifts in the fine structure constant. Proposals envision clock arrays as sensors of passing gravitational waves and ultralight dark matter. In the heavens, millisecond pulsars mark their rotations with a regularity rivaling laboratory oscillators. Correlations among their arrival times have begun to trace a nanohertz chorus consistent with gravitational waves from binary black holes. With time and sensitivity, the same method could hear a murmuring background from the early universe. Each technique tests whether time in practice obeys time in theory, whether the local tick and the cosmic talk are pages of the same book. The escalation is less a rise in volume than a narrowing of options. The early universe cannot be a featureless blank. Its fossil light proves otherwise. Nor can it be an arbitrary state among many. The arrow and the uniformity forbid that as well. It must be special in a way that is lawful. A mechanism must set entropy low without fine-tuning, smooth horizons without erasing structure, flatten space without a cosmic coincidence, and leave behind signatures subtle enough to be missed, so far yet robust enough to be found soon. If general relativity's singularity is replaced, the replacement must carry an architect for order. If symmetry is the architect, it must be precise enough to shape initial conditions, yet generous enough to birth diversity. If information knits geometry, then the first stitch must be describable, not mystical, a calculable threshold at which correlations acquire a macroscopic notion of before and after. The mystery deepens because progress has cornered it. Precision does not disperse wonder here, it distills it. Better maps of the microwave sky accentuate the need for an early mechanism. Tighter bounds on primordial tensors sharpen the silhouette of any pre-recombination dynamics. Galaxy surveys and lensing reconstructions refine the late-time stage on which the origins choices play out. Neutrino oscillations, mass hierarchies, and possible sterile cousins link laboratory experiments to the first seconds. Black hole thermodynamics and holographic dualities, developed far from cosmology, circle back to question what a beginning can mean when geometry is bookkeeping for entanglement. In this light, the Big Bang is no longer just an explosion but a constraint, a surface in theory space where geometry, matter, and information meet. Whether it is a bounce, a no-boundary cap, a tunneling event, or a symmetry junction, its task is the same: to explain why a universe capable of clocks, memory, and causality could arise at all, and why it did so with a precision that permits galaxies and minds. The crack in the timeline is not a flaw, it is a seam where two fabrics overlap. Pull gently, and the weave beneath reveals itself. Pull harder, and the question that began as a number becomes what it always was: an inquiry into why there are moments for numbers to live in, and why those moments march in one direction from a beginning that still withholds its final word. Theories gather at the edge of the map like ships at fog's border, lanterns dimmed, hulls creaking with different answers to the same unspoken question. Each offers a way to step past the classical cliff, to cross the line where general relativity's coordinates run out, and the grammar of time itself becomes uncertain. None is proven. All are disciplined by what the sky already says. Together they form a quiet parliament at the beginning, speaking in equations about how a universe learns to count. The most austere voice keeps the boundary sharp. In this picture, general relativity is trusted as an effective theory, astonishingly accurate within its domain and honest about where that domain ends. The initial singularity is not matter piled to infinity but a domain wall in theory space, a place where curvature would diverge, geodesics terminate, and the classical manifold ceases to make sense. Time in this view exists only within spacetime. Asking for a before is like asking for a north of the North Pole. The cosmos opens as a page already written with its first line, and the mystery is not what happened previously, but what rules set the first sentence. This stance wears no ornament, no preface, no prehistory, only the confession that a deeper description must replace the classical one at t right arrow 0, while the classical story remains sovereign everywhere else. Another lantern burns with a smoother flame. Inflationary Genesis imagines that, in the universe's first instance, a scalar field dominated the energy budget and drove space into a burst of accelerated expansion. In a fraction of a second, horizons stretched so far that regions now on opposite sides of the sky could once have shared the same thermal past. Curvature was driven toward flatness. Quantum fluctuations of the field, magnified to cosmic scales, became the seeds of galaxies. The near-scale invariance and Gaussian statistics of the cosmic microwave backgrounds ripples fit this music with surprising fidelity. Yet even this melody has unresolved chords. The shape of the inflatten's potential, the mechanism that ends the burst and reheats the universe, the reason a suitable patch existed at all remain open. In some realizations, inflation never truly ends but continues elsewhere, budding pocket universes in a fractal sea. Local time then appears to begin with each bubble's nucleation, while the global picture, if global even has meaning, becomes timeless, measure-laden, and difficult to define. A different elegance removes the cliff by rounding it. The no-boundary proposal of Hartle and Hawking recasts the earliest stage as a finite, boundaryless geometry in Euclidean signature, where time behaves like a spatial direction. Near the origin, the manifold closes smoothly like the surface of a sphere near a pole. Crossing a mathematical seam, Lorentzian time switches on, and the familiar causal structure blooms. There is no singularity, no earlier edge, only a compact beginning whose simplicity is selected by a path integral over geometries weighted by action. The arrow of time then emerges as the universe expands and classical histories become highly probable. The challenge lies in making the sums precise, in tamming measure and contour, and in tying the construction to concrete predictions that differentiate it sharply from other graceful starts. A neighboring proposal keeps the quantum spotlight but changes the staging. In Vilenkin's tunneling from nothing scenario, the wave function of the universe describes a transition from nothing, not empty space, but the absence of classical spacetime, to a small, closed geometry that then inflates and grows. Tunneling probabilities depend on the potential landscape and the choice of boundary condition. Different prescriptions weight different beginnings. As in the no-boundary view, classical spacetime is not extended past the origin. It condenses from quantum possibility. The disputes here are technical but consequential. Which boundary condition, which measure, which contour truly captures the genesis, and how those choices echo in observable parameters, tensor amplitudes, curvature, non-Gaussianities, that the sky can adjudicate. Some theories choose not to end the story at all. Bounce cosmologies seek to replace the singularity with a turnaround. A prior contraction smooths irregularities under a stiff equation of state, and a transition, quantum or brain-mediated, launches expansion. In loop quantum cosmology, the discreteness of quantum geometry bounds curvature and energy density. As the Planck regime is approached, effective repulsion appears and a bounce occurs. The scale factor never vanishes. Time extends through the neck, symmetric or not. Ekpyrotic and brain world models picture higher dimensional brains colliding or passing, with a slow, ultra-stiff contraction ironing anisotropies before a fire of reheating. These scenarios naturally address horizon and flatness without an inflating phase, but they must contend with matching conditions across the bounce, with generating the observed nearly scale-invariant, adiabatic Gaussian perturbations, and with avoiding instabilities when matter and geometry trade roles at the transition. Another lantern carries a cyclical hallmark. Conformal cyclic cosmology imagines that the remote, exponentially stretched future of one universe can be conformally rescaled, erasing mass scales as all particles asymptote to light-like behavior, and identified with the Big Bang of the next. Eons follow eons, each separated by a conformal mapping that makes the hot beginning and the cold end mathematically rhyme. In this view, the vanishing of the whale curvature at the origin is not a miracle but a geometric necessity of the matching. Black hole evaporation in the previous eon seeds subtle imprints, perhaps concentric low-variance circles, in the next eon's microwave sky. The proposal is bold and controversial. Claimed signatures remain debated. Yet its ambition is to shift low-entropy beginnings from assumption to consequence, enforced by the way geometry forgets scales at infinity. Symmetry extends even to time itself. In CPT-symmetric cosmologies, the Big Bang is a central, low-entropy junction from which two mirror universes expand in opposite temporal directions. Charge conjugation, parity inversion, and time reversal combine to make the total state highly symmetric, the arrows of time in each half point away from the junction, so both sides experience a forward flow and increasing entropy. In some models, this structure explains matter, antimatter asymmetry, and offers dark matter as a right-handed neutrino produced gravitationally at the bang. It predicts sharp patterns in the neutrino sector, mass hierarchies, perhaps one nearly massless species, and suppresses certain primordial gravitational wave signatures. Here the beginning is not erased but doubled, its specialness encoded as a symmetry rather than a coincidence. Other proposals move the spotlight from geometry to information. If quantum correlations are primary and geometry is a code that organizes them, then time may emerge as a parameter that tracks change in entanglement rather than a fundamental coordinate. The page, Wooter's mechanism, recovers dynamics within a timeless global state by conditioning on the state of a clock subsystem. The thermal time hypothesis derives a preferred flow from the statistical state of a system via modular theory. Holography deepens the intuition. In AD-SCFT duality, the entanglement structure of a boundary quantum field theory encodes bulk geometry. Areas of extremal surfaces measure entanglement entropy, and islands recover the unitary page curve for evaporating black holes. In such a world, the beginning could be a phase transition in informational order, a percolation of entanglement that births a classical spacetime and installs an arrow through decoherence and coarse graining. Predictions here are subtle, correlations across horizons, specific patterns in quantum chaos and complexity growth, and constraints on parity-violating imprints in primordial fields that couple to action-like degrees of freedom. Discreteness has its own advocates. Causal set theory posits that the fundamental structure is not a continuum, but a partially ordered set of elementary events, with the order capturing causality and the number of elements giving volume. Order plus number equals geometry. Spacetime emerges statistically from a vast sprinkling of relations. The beginning in this register is the onset of order growth, perhaps via a classical sequential growth dynamics or a quantum generalization. Lorentz invariance is preserved statistically. Continuum pathologies like singularities may be avoided because the underlying structure never supports infinite curvature. Observable consequences could appear as Poisson fluctuations in light cone volumes, in minute violations of locality, or in specific spectral features of primordial perturbations seeded by discrete birth. Another route keeps the continuum but tames the ultraviolet. Asymptotic safety proposes that gravity's renormalization group flow approaches a non-trivial fixed point at high energies, rendering the theory predictive and finite. Near the Planck regime, couplings run to scale invariant values. Cosmology inherits dynamics that can mimic an inflation-like smoothing or alter the primordial spectrum without introducing new fields. Singularities may be avoided because the extrapolation of classical couplings to infinity is replaced by fixed-point behavior. The beginning becomes a crossover in scaling, not a breakdown. Tests would live in the tilt and running of the power spectrum, in relations between scalar and tensor modes, and in the interplay between laboratory gravity measurements and early universe extrapolations of the same flow. A final lantern rearranges the variables. Shape dynamics rewrites general relativity by trading refoliation invariance for local spatial conformal symmetry. Dynamics unfolds in terms of evolving spatial shapes, with a preferred global time parameter related to the mean extrinsic curvature, York time. The beginning is reframed not as a coordinate singularity, but as a special configuration in the space of shapes, perhaps one of minimal complexity or maximal symmetry. Entropy's arrow could then be tied to the growth of shape complexity rather than to a separate boundary condition. If correct, familiar observables remain, but their interpretation shifts. Cosmological initial data would be constraints on shapes, and the low entropy past might be geometrically natural in this new language. Across these visions runs a shared demand: prediction. Each must face the same telescopes and the same fossils. Inflationary and bounce models make promises about the tensor spectrum, the amplitude and tilt of primordial gravitational waves, whether parity is violated, whether chirality reveals action-like couplings. Many scenarios shape non-Gaussianity, local, equilateral, orthogonal patterns in three-point functions, and seed isocurvature modes that violate single-clock expectations. Actinic fields and parity-violating interactions can rotate polarization, producing cosmic birefringence in the microwave background. Topological relics, cosmic strings, domain walls, would write line-like discontinuities or stochastic gravitational backgrounds. Neutrino sector predictions differ. Extra light species raise the effective NF. Specific mass hierarchies or a nearly massless eigenstate would echo in laboratory oscillation results and in structure formation cuts. Some models permit primordial black holes with distinctive mass spectra. Their abundance constraints fold back on the shape of the earliest fluctuations. Even the controversial claims, concentric low-variance circles, anomalous alignments, serve as touchstones. If real, they must be explained. If not, their absence tightens the noose. The lanterns do not extinguish one another. They cast overlapping light onto the same mist, revealing different textures in the fog. The classical boundary insists on intellectual humility. Inflation paints a sky that closely resembles the one observed. Bounces promise continuity without infinities. Symmetry offers an origin as junction rather than edge. Information hints that time is a property of correlation, not a substance poured into a container. Discreteness removes the very platform on which singularities stand. Fixed points keep the ultraviolet from erupting. Shape dynamics rearranges what counts as chain. The cosmos will choose or has already chosen, and the choice is traceable in polarization curls, in the statistics of ancient hydrogen, in the hum of spacetime, in the masses of ghostly neutrinos, and in the silence where signals should be but are not. When the measurements are fully composed, the beginning will cease to be a metaphor and become a mechanism, an answer carried not by philosophy alone, but by the sky's own handwriting. The instruments of the present lean toward the first light like listeners at a doorway, attuned to murmurs that crossed billions of years. Each one is built to test a different syllable of the beginning, to separate what must be true from what is merely beautiful. Together, they form a quiet constellation of experiments, drawing a lattice across sky and earth where a theory of time's birth must fit or fail. In Antarctica and on high plateaus, telescopes stare into the cold, combing the ancient afterglow for a curl that should not be there. Bicep and Keck have learned to read the cosmic microwave background not only in temperature, but in polarization, the faint orientation of the remnant light scattered when the universe was young. The Simons Observatory gathers a fleet of dishes and cameras to map that polarization across wide fields, hunting the telltale B-mode swirls that primordial gravitational waves would have drawn. Dust in the Milky Way complicates the script. Lensing by intervening matter converts one pattern into another. The signal, if it exists, is a whisper below the weather of the galaxy. Yet the method is patient. Delensing techniques subtract the distortions. Multi-frequency observations peel away foregrounds like veils. Beyond the horizon of construction, two experiments hold the promise of verdicts. Lightbird, a satellite tuned for polarization with a singular devotion, and CMB-S4, a ground-based array designed to push sensitivity to the threshold where a universe that inflated loudly cannot hide. If a primordial tensor background is present, they aim to weigh its amplitude, to measure its tilt, to check whether the earliest waves break parity and leave a handedness in the sky. Even a continued silence is a result, turning down the volume on many beginnings at once. On larger scales, the universe keeps its own yardsticks and rulers. Daisy threads a spectroscopic net through millions of galaxies and quasars, measuring their recession with such precision that the faint ridge of baryon acoustic oscillations, the sound horizon fossilized in matter, appears as a standard ruler in 3 dimensions. Euclid, watching from space, sketches weak gravitational lensing across a wide swath of sky, a gentle shearing of galaxy shapes that reveals the distribution of dark matter and the growth of structure through time. The Nancy Grace Roman Space Telescope will add deep infrared eyes to that effort, mapping lensing and supernovae with the calm cadence of a spaceborne surveyor. On the ground, the Rubin Observatory's legacy survey of space and time is poised to film the sky, revisiting every patch again and again, measuring not just positions but histories. Light curves of distant explosions, motions of asteroids, subtle drifts in lensing patterns that betray the weight of the cosmos between us and the far. Together, these projects trace the growth of cosmic scaffolding, how perturbations laid down in the first instance became the web of galaxies, and test whether gravity's large-scale grammar matches Einstein's, whether the expansion history inferred from the earliest light truly harmonizes with the song of the late universe. Elsewhere, the cosmos is approached at a different wavelength, a radio line from neutral hydrogen that once filled the dark between the first stars. Hera assembles radio dishes into an ear for the age when the first ultraviolet photons switched on, when bubbles of ionized gas ate into a cold, neutral sea. Chime and its planned sibling chord widen the bandwidth and field of view, listening for structure in the 21-centimeter line across cosmic time. The square kilometer array, rising in stages, will extend the reach from the epoch of reionization toward the true dawn, aiming at a tomography of the young universe. Not a single snapshot, but a film of hydrogen growing warm, bright, and then transparent. In those patterns lie backlit clues to pre-recombination physics, how the initial power spectrum behaved on scales too small for the microwave background to resolve, whether interactions beyond the standard model chilled the gas or brightened the radio fog, whether the timing of the first light agrees with a beginning that was smooth or a beginning that was rough. Where light is mute, gravity speaks. Interferometers have already learned to hear the last seconds of black hole and neutron star binaries, converting the trembling of spacetime into sound. LIGO, Virgo, and KAGRA accumulate a calendar of mergers, and by their continued quiet at the right frequencies, set upper bounds on any stochastic background loud enough to rattle their arms. The absence of a roar trims back the parameter space for cosmic strings and violent early-phase transitions. A new instrument waits in blueprints and clean rooms. LISA, a triangle of satellites separated by millions of kilometers, will drift on heliocentric orbits and hear waves thousands of times longer, where white dwarf binaries sing, and where cosmological murmurs from the first fractions of a second might reside. Farther in the future, third-generation ground detectors, Einstein telescope and cosmic explorer, would press sensitivity much deeper, able to stack signals into a background measurement and to test whether spacetime ever carried an ancient hum. If a primordial gravitational wave spectrum is found, it will be less a memory than a fingerprint. Yet even a fingerprint can convict. Energy scales, symmetries, and mechanisms would narrow to the few that can shake the cosmos so early and so well. The youngest galaxies become witnesses by their very surprise. Infrared deep fields resolve objects whose redshift places them within a few 100 million years of the beginning. Their masses, star formation rates, and morphologies test how quickly complexity can emerge. Sometimes the counts run ahead of expectation, suggesting that small-scale power or early cooling was kinder to structure than standard models assumed. Strong gravitational lensing by foreground clusters turns the universe into its own telescope, magnifying infinitesimal smudges into readable texts. Weak lensing surveys add the context of the mass that shapes them. The timeline of reionization, how quickly the fog burned away, feeds back into the first pages of cosmology, constraining the abundance of early halos and the efficiency of star formation seeded by initial conditions. Here, too, the narrative must keep its promises. A beginning that sets fluctuations and an expansion that grows them must not only fit the microwave background, it must pass the audit of the very first cities of stars. Ghostly particles carry messages from epochs light cannot reach. IceCube watches a cubic kilometer of Antarctic ice for flashes that announce a neutrino's rare collision, tracing lines back to blazars and perhaps to more exotic engines. Its proposed Gen 2 expansion would sharpen vision across higher energies and larger volumes. Juno and Hyperkamiakin, filled with immaculate liquids and water, chase oscillations with a fidelity that pins down mass ordering and mixing angles. Together with cosmological data, those measurements set how neutrinos tweak the growth of structure and the expansion rate. A more audacious dream targets the cosmic neutrino background itself. Ptolemy hopes to capture the faintest whisper of relics from when the universe was seconds old, colder than the microwave sea and more difficult to touch than any other fossil. If such a detection is made, the thermal ledger of the first moments would add a new line item, and any extra light species, dark radiation, would require a place in the accounting. Closer to home, time becomes a laboratory. Optical lattice clocks now compare seconds it parts in. 10 raised to 18 and beyond. Lift one by a centimeter, and gravity shifts its song enough to hear. Networks of such clocks, linked across continents, test Lorentz symmetry and CPT invariance with an exactness that leaves little room for departures. They also promise a novel ear for passing gravitational waves at frequencies that bridge ground interferometers and pulsar timing arrays. Atomic interferometers, projects like AION and ELGAR, drop ultra-cold atoms through long shafts of vacuum and read-out phase shifts with a precision that turns acceleration, rotation, and spacetime curvature into measurable quantities. In the sky, millisecond pulsars serve as metronomes so steady that correlated jitters in their arrival times reveal a nanohertz background, likely from billions of years of supermassive black hole binaries. The International Pulsar Timing Array coordinates telescopes across hemispheres to grow that sensitivity, and with time, the same technique could listen for cosmological backgrounds spread thin across the longest waves. Each null test is a confirmation. Each deviation would be a door. Particle physics remains the workshop where hypothetical fields earn or lose their names. The High Luminosity Large Hadron Collider extends the reach for rare processes and subtle couplings, examining the Higgs boson not as a trophy, but as a portal. If it speaks to an inflaton-like field, if it bows to hidden sectors, if CP symmetry fractures in places unseen, the cracks may tell of baryogenesis or of dynamics that help set the initial conditions. Proposals for future colliders, linear or circular, lepton or hadron, sketch paths to higher energies or to precision campaigns where tiny departures from the standard model could signal a larger world. Searches for light relics and dark photons, action-like particles and sterile neutrinos, place experimental fingers on parameters that cosmology also feels. Chemistry from the first minutes, nucleosynthesis yields, tightens these loops. Any change to the expansion or particle content then must be paid for in deuterium and helium, in the power spectrum of the microwave background, in the mass function of the smallest galaxies. All these instruments are threads. The pattern emerges only when they are woven. Joint analyses, CMB with large-scale structure, gravitational waves with galaxy catalogs, 21-centimeter tomography with reionization histories, pulsar timing with lensing and clocks, break degeneracies that let different beginnings masquerade as twins. A slight excess in the effective number of relativistic species would push in one direction. A measured tilt in the tensor spectrum would pull in another. A birefringent rotation of polarization would announce parity violation in the early universe. A stochastic background at millihertz would prefer a first-order phase transition or a network of strings. A confirmed departure in the small-scale power spectrum might favor a bounces prehistory. The absence of primordial tensors to very low levels could lean against many inflationary potentials while leaving room for no boundary or CPT-symmetric starts. The goal is not to crown a philosophy, but to reduce the possibilities until one remains that explains with economy and predicts with courage. In the end, the scientific tools are not merely machines. They are commitments to a way of listening, that nature will answer in consistent tones across different instruments, that the origin of time is not a rumor but a measurable event, or boundary, or transition, whose fingerprints can be read. The sky offers polarization curls and lensing shears. The Earth offers clocks and interferometers. The universe offers neutrinos and gravitational waves as couriers that do not tire. What began as myth is pressed, gently but insistently, into numbers. The first moment will not be seen. It will be inferred, encircled by evidence until only one path leads inward. And on that path, theory must walk in step with measurement, until the grammar by which moments came to exist is no longer guessed, but known. A beginning without a before is not an explosion. It is a rule. In such a picture, origin is written as a boundary condition rather than an episode, a sentence that determines how every sentence after it can be formed. Time becomes the grammar of existence, the order by which events can be conjugated, the syntax that lets causes assemble into consequences, the cadence that allows change to cohere. If general relativity draws a manifold where geodesics thread possible histories, then a beginning that is not in time but of time stands as the axiomatic first line, the constraint that makes narrative possible at all. Classical gravity hints at this reframing. Its singularity at the origin is not a shard of matter but the place where the classical chart fails. The coordinates fold and the curvature climbs beyond trust. Quantum ideas step in to soften or replace the cliff, no boundary caps, bounces, tunneling events, symmetry junctions. But in all these renderings the notion persists. The birth of time is a condition, not a memory. The difference is not semantic. An event invites a before. A rule explains why before is an empty set. The universe is then like a globe near a pole. Directions exist, but certain questions about earlier bearings lose meaning because the map has changed category. The arrow that runs through every life receives its permission from that first rule. Entropy is the storyteller. It points the plot forward because there are more ways to be disorderly than to be arranged. Yet gravity complicates the simple arithmetic. A smooth early cosmos, measured by the near-isotropy of the microwave background, corresponds to astonishingly low gravitational entropy, because the swollen catalog of high-entropy states includes clumped configurations, tidal tangles, and black holes. Penrose gave this astonishment its sharpest edge. The early whale curvature was effectively zero, as if the fabric had not yet learned to wrinkle. No consensus mechanism inside the standard hot Big Bang sets that value. The arrow emerges only if the past is special, and the specialness is precisely what the origin must account for. From such asymmetry, memory is distilled. Records are physical. They require irreversible processes, leftovers that cannot be unbaked from the loaf. A ripple fossilized in the cosmic microwave background, a zircon grain housing uranium's slow confession, bits flipped in silicon by a flow of electrons. All are residues left by entropy's climb. Decoherence, working patiently at scales large and small, selects durable histories by bleeding quantum superpositions into their environment, until the fragile possibilities become robust alternatives. Causation in this landscape becomes a pattern that holds. Interventions matter because the world-state space is threaded in a way that preserves traces from past to future. The existence of records is the proof of an arrow. The paucity of records in the beginning is the mystery the arrow leaves behind. Human time is braided from different fibers than cosmic time, yet both are spun from the same loom. Biological clocks tick in proteins and ions, circadian rhythms entrain to daylight and drift in caves. Cultural time counts harvests, rains, revolutions. Calendars renovate themselves to keep faith with the sky. Now, optical lattice clocks compare seconds at parts in 10 raised to 18, sensitive enough that lifting one a hand's breadth changes its song. Millisecond pulsars mark rotations with the obstinate regularity of crushed diamond. Between a heartbeat and a billion years lies a continuum of measures, all built from matter that the early universe forged. Humility follows. Instruments fashioned inside the story are used to reconstruct the prologue. Clocks made of stardust test the rule that allowed clocks to exist. If time is not a substance but a relation, then the origin is the loom, the onset of relations that admit succession. Several frameworks suggest this turn. In the page, Wooter's mechanism, a timeless global quantum state contains subsystems that serve as clocks. Conditioning on a clock's reading pulls a sequence from stasis. The thermal time hypothesis argues that a statistical state induces its own preferred flow via modular dynamics, hinting that time can arise from information-theoretic structure rather than geometry. Holography pushes the intuition further. In the best-studied dualities, the entanglement pattern of a quantum field theory encodes a gravitational spacetime. Areas of extremal surfaces count entanglement entropy. The island formula restores unitarity to evaporating black holes and lets their page curve turn as expected. In these vistas, the beginning becomes a phase transition in connectivity, a crossing of a threshold beyond which correlations arrange themselves so that distance, duration, and cause acquire meaning. Elegance stands next to contingency at this frontier. Some origin stories attempt necessity, symmetry at the junction, CPT mirrored across the bang, could force low entropy and fix particle properties with grace. Some argue for dynamics. Inflationary smoothing or an ekpyrotic contraction irons irregularities by lawful pressure. Others allow selection. A landscape of vacua or many eons with different constants would leave habitable regions to be observed precisely because they permit observers. Necessity satisfies a deep aesthetic. Contingency honors the stubborn fact that laws are measured rather than decreed. There is room for both. Mathematics supplies coherent blueprints. Measurement constrains which blueprints are realized. Wonder remains in either case, because the fit between intelligible law and fertile world is itself a surprise that resists exhaustion. Open questions preserve the space in which wonder breathes. What fixes the low entropy past? Geometry, symmetry, dynamics, or an information-theoretic principle yet unnamed? Do primordial gravitational waves exist at any level accessible to the ears being built? And if so, Do they hum with a tilt that anchors an energy scale for the first instance? Is cosmic birefringence an instrument's dream or a signature of action-like fields twisting polarization by a tiny angle across the sky? Does the effective number of light species, distilled from the damping tail of the microwave background and from deuterium's exactness, stay with the standard model or lean toward extra radiation near the first minutes? Is the Hubble tension a parallax of understanding or a relic of physics that briefly visited the plasma before recombination? Are the earliest galaxies genuinely too massive too soon, or do dust, lenses, and templates conspire to mimic urgency? Each query points backward, without pretending that answers must shout. Many of the truest answers arrive as silences that forbid alternatives. The ethical posture of this search is patience. Experiments do not measure beginnings directly. They outline constraints that any beginning must obey. Polarization curls and lensing shears, nanohertz choruses and millihertz murmurs, deuterium counts and helium whispers, neutrino masses and mixing angles, clock comparisons and atomic phases. These are the glyphs in which the prologue is written. Theories earn their keep by foretelling which glyphs should appear together. Inflation consistent with small tensors and Gaussianity, bounces that predict distinct non-Gaussian shapes, no boundary caps that favor specific spectra, CPT-symmetric junctions that correlate neutrino hierarchies with dark matter candidates, emergent time proposals that imply subtle parity violation or cosmic birefringence. Each carries signatures, sometimes faint, sometimes loud. Degeneracies are broken by synthesis. What cannot be mimicked by alternatives hardens into truth. The philosophical weight of a beginning without a before falls not on chronology but on meaning. If origin is a rule, then why now dissolves into why this rule. A question about why the universe chooses a grammar that allows complexity, memory, and life. There is no logical obligation that a cosmos support chemistry with long-lived nuclei, stable atoms with rich spectra, or stars that burn slowly enough to seed clouds and worlds. Yet the measured constants and initial conditions combine to allow such theaters to appear. Fine-tuning arguments, anthropic reflections, and multiverse speculations orbit this fact. But even without a final verdict, the lesson is clear. Possibility is structured. The boundary condition at the beginning did not merely open a future. It selected a kind of future in which narratives can be told, fossils can be read, and questions can be asked. In the quiet of that recognition, all persists without superstition. A universe can be lawful without being simple, intelligible without being tame. It can be ancient and still ripen new mysteries as instruments sharpen. It can teach that before is sometimes the wrong word, that grammar matters as much as lexicon, that the deepest realities are not objects but relations. These are not retreats into metaphor. They are what the measurements imply when taken seriously across their entire span. What remains unfinished is not the effort but the drawing of its lines to convergence. A low entropy past awaiting a lawful cause, a stochastic gravitational background that may yet be heard, a polarization curl that could fix a scale, a drift in a constant that might betray new fields, a neutrino property that would bind laboratory and sky into one equation, an anomaly that survives every cross-check and demands a new chapter. Each is less a promise than an invitation. Theories will continue to walk toward these beacons. Tools will continue to refine the questions into numbers that prefer one map over another. The work is cumulative but not mechanical. It proceeds by eliminating what the universe has never done and keeping what it might. The final cadence belongs to continuity, not closure. The search does not aim to timestamp the first moment and then file the case. It seeks an understanding of what it means for moments to exist. A beginning without a before can be learned by a species that arose long after, using clocks that tick because the beginning permitted ticking, reading light that traveled because geometry allowed travel, asking questions because entropy made memory possible. In doing so, a curious fact comes to light. When a universe becomes capable of contemplation, the boundary condition that authored time acquires a mirror. Through minds made of its own matter, the cosmos reflects upon its dawn. The rule that lets stories begin becomes the subject of a story, and in that telling the origin does not change, but awareness reaches back, and the universe for an instant knows that it has begun.